During this webinar, we will investigate what selectivity is, how it's influenced, and why it's one of the most effective factors to change for enhancing resolution. We will provide an overview of various reverse phase HPLC phase chemistries available on the market and discuss the importance of a column toolkit for delivering orthogonal selectivity, with examples of screening various phase chemistries. In addition, we will explore superficially porous particle columns, which are currently gaining momentum in industry. But how do these differ to fully porous particle columns, and what benefits can they actually provide to your method development? The majority of HPLC analyses are performed in reverse phase mode. The C18 is still the workhorse for many applications, but its dominance has reduced as the complexity of samples has increased, and also with increasing polarity. It has broad applicability for pharmaceutical, food, and environmental analyses. However, C18 columns cannot be used for everything, and is the reason for phases with orthogonal selectivities. Various stationary phase chemistries are coming out regularly to help solve customer challenges. There is a definite emergence of helic chromatography in recent years due to the growing need for the analysis of polar compounds, and AQ columns are gaining momentum for this reason too. Additionally, there is a continuing trend for faster analysis without compromising column lifetime, and we've seen the development of what is termed SPP, or superficially porous particle columns. One of the most important things in HPLC is to obtain the optimum resolution in the minimum time. A resolution value of 1.5 or greater between two peaks will ensure that the sample components are well separated to a degree at which the area or the height of each peak may be accurately measured or integrated. A value of 1.5 is baseline resolution, with a value of 1.2 being highly desirable during method development. Chromatographic resolution is determined by three key parameters: efficiency, retention, and selectivity, and this is the basis of the fundamental resolution equation shown on the slide. Retention can be altered by changing parameters like the stationary phase and the mobile phase. Resolution can be improved by increasing the retention, but this will result in longer analysis time, wider peak widths, and lower sensitivity. An example of altering retention using C18 and C8 phases for neutral compounds is shown on this slide, and you can see that the C8 phase results in much reduced retention and a decrease in resolution. Column efficiency, or plate number, N, is a physical measure of band spreading in a separation. Higher efficiencies provide sharper and narrower peaks, resulting in higher sensitivity and improvements in resolution. Efficiency can be quite easily increased by using a longer column length or using a column packed with smaller particles, and an example is shown for 5 micron and 3 micron C18 columns. However, as shown in the equation, resolution only increases with the square root of the plate number. Finally, and usually most effectively, the selectivity can be changed to achieve changes in resolution. Selectivity refers to the ability to distinguish between sample components and is measured as a ratio of the retention factors, or K values, of two analyte peaks. Now, high selectivity, or alpha values, indicate good separation between the apex of each peak. However, the alpha value is not directly indicative of the resolution, as efficiency could also come into play. An increase in alpha can result in greater resolution, sometimes in a similar amount of time, and with the same or changed elution order. Variables which affect selectivity include the stationary phase and the mobile phase, which I'll go into in a bit more detail on in a few slides' time. And as a quick example, this slide shows a C18 and a C18 PFP column run under the same conditions, which demonstrates a change in elution order and no coelution on C18 PFP. All three factors in the resolution equation are important. The selectivity is considered the most effective term to change to achieve the desired resolution, which this graph demonstrates. In terms of retention, the largest gain in resolution is achieved when the retention factor K, or relative retention, is between 1 and 5. Above a K value of 5, increasing the retention provides only minimal increases in resolution. The useful range can then be extended between 2 and 10 for more complex sample mixtures. Efficiency is easy to change, however, resolution only increases by the square root of the plate number. In comparison, relatively small changes in alpha or selectivity values lead to considerable changes in the resolution, which the graph demonstrates with a nearly linear relationship. So I mentioned previously that selectivity can be influenced by the mobile phase and the stationary phase. There are many factors for the mobile phase which can affect selectivity, including the mobile phase pH and the additive type and concentration, for example. These types of operational variables can contribute to more error because they're cumulative, so it is desirable to keep the mobile phase as simple as possible so that methods are easier to reproduce between labs. Choosing an alternative column chemistry is considered one of the most powerful and simplest ways to alter the selectivity of a separation. Variations in stationary phase chemistries can provide alternative modes of interaction and retention characteristics, which in turn may simplify method development and reduce the need for mobile phase additives. Initial screening of columns containing different bonded phases under the same mobile phase conditions can help achieve the desired separation more quickly, therefore increasing productivity. It is, however, important to define the scope and the attributes of the methods being developed to carry out the appropriate screening methods and also know when to stop optimization. So why are C18 phases used? They remain the go-to column of choice for reverse phase LC separations, as they have excellent performance for a broad range of analytes, and they have long-standing proven stability over a wide pH range, as well as a range of mobile phases and additives. Some laboratories may choose to simply use a C18 phase because of previous success with other analytes, or because of column availability in their lab. But when is it advantageous to try another bonded phase chemistry? Again, it's useful to screen a number of phases during initial method development. Other bonded phase chemistries are also useful when you have poor retention or resolution of polar compounds, even when using a highly aqueous mobile phase. They can provide solutions for very hydrophobic compounds if you have too much retention, for example. And additionally, other phases can provide solutions for resolving isomers or closely related species, which may otherwise require complex method development. So what are some of the reverse phase chemistries available today? This shows a small snapshot. The standard workhorse C18 phase has C18 alkyl ligands bonded to the surface of the silica with hydrophobic end capping. As a result, the major retention mechanism is dispersive interaction, whereby the retention is proportional to the hydrophobicity of the molecule. The C8 phase is another common phase and is less hydrophobic, resulting in less retention than C18 for more hydrophobic compounds. They are particularly useful for lipids and steroids. AQ-type columns are rapidly becoming the second most popular phase after C18 to aid the retention and separation of more complex polar analytes, and can also offer alternative selectivity. These phases typically have a polar end cap, allowing robust operation under 100% aqueous mobile phase conditions. They can facilitate dipole-dipole and hydrogen bonding interactions between the analyte and the stationary phase, as well as hydrophobic interactions. RP-amide phases can also aid retention for polar compounds. They have a polar group embedded within the alkyl chain, which facilitates alternative selectivity, and you can also use with 100% aqueous mobile phases. Cyanophases will allow pi-pi interaction, moderate hydrophobic interaction, and the strong dipole of the cyano group facilitates dipole interactions with polar solutes. The phase offers decreased retention for hydrophobic compounds in comparison with standard alkyl-bonded phases due to reduced hydrophobic character. Cyanophases are often used for improving polar compound separation and can be used in both reverse phase and normal phase chromatography due to its intermediate polarity. If small polar molecules still do not retain, then Hillic is a suitable alternative, and these phases typically consist of either classical bare silica or silica modified with polar functional groups, such as diols. Amino columns offer high polar retention and are an ideal choice for analysis of compounds with weak ion exchange capacity, and they're particularly suited for the analysis of carbohydrates. Phenol and pentafluorylphenol, or PFP phases, allow unique selectivity for aromatic amylides. They're particularly good for phenolic-containing compounds, closely related species, and also metabolites. The phenol-type phases contain electron-rich aromatic rings, whilst the PFP phases, on the other hand, have electron-deficient rings due to the electronegative fluorine atoms present. Additionally, the carbon-fluorine bond in the PFP phases is very polar, facilitating hydrogen bonding and dipole-dipole interactions between the electronegative fluorine atoms and the analyte. Finally, phases such as the C18 PFP, which utilize a mixture of C18 and PFP ligands, facilitate alternative selectivity over traditional C18 phases due to the mixed mode interactions. The phase provides steric selectivity, pi-pi interactions, and also hydrophobic interactions, which is particularly useful for closely related species and metabolites. So how can these different phases impact the chromatography? In the next few slides, I'll show a couple of examples of initial screening of various stationary phase chemistries using fully porous columns. The first method development example is the screening of 6 stationary phases of the same dimensions using the same mobile phase conditions for a mixture containing the following 9 compounds. A simple gradient program was carried out with a mobile phase containing water and acetonitrile with 0.1% formic acid. This slide shows the results of the screen. You can quickly see that for this particular group of compounds, some phases caused larger changes in selectivity than others. In this example, the quasar C18, C8, and AQ columns showed similar retention profiles for these compounds and the same elution order. Screening of the AQ plus column showed greater changes in selectivity. Compounds 1 and 2 showed much reduced resolution, no longer being baseline resolved, and additionally compounds 4 and 5 co-elute. The quasar cyano resulted in large changes in selectivity and elution order due to the electrostatic interactions offered by this phase chemistry. Reduced retention was also reserved due to its reduced hydrophobic character. The change in selectivity and reduced retention has not been beneficial in this case, with less than baseline resolution and co-elution of some compounds. The quasar biphenol phase, on the other hand, provided excellent separation and with greater resolution in comparison with the C18. In addition, changes in selectivity and elution order were observed. The biphenol phase will offer hydrophobic, pi-pi, and also steric characteristics, allowing unique selectivity for aromatic-containing analytes and closely related species. So initial screening of various column stationary phase chemistries is a very powerful and quick approach in method development to observe changes in selectivity. Another example I would like to share is the use of AQ columns for polar compounds in comparison with a C18. In this example, a C18, AQ, and AQ plus column have been run under the same conditions. The C18 column has C18 ligands and non-polar end capping. The AQ column has C18 ligands and polar end capping, and the AQ plus column has proprietary end capping and bonding with polar functionality. On the C18 column, compounds 2 and 3 co-elute. However, on the AQ column, they start to separate. To increase the resolution and improve the retention further, you can increase the aqueous content of the mobile phase, and I'll show an example of this analysis being optimized on the next slide. But the addition of a polar end cap will provide a high degree of polar character to the final alkyl bonded phase, and that results in a second mechanism and the potential to provide alternative selectivity. Now, if we go one step further and run the same analysis on a AQ plus column, there is a larger change in selectivity. Compounds 2 and 3 have achieved more than baseline resolution, and there is greater resolution between compounds 4, 5, and 6. The elution order has also altered, and much greater retention has been achieved. The runtime could be reduced by altering the mobile phase composition too. It is, however, necessary to define the goal of your screening and the attributes of your desired method. For example, is the goal to have a quick screen to know instantly which column you should move forward with, or is it more of an investigative screen to determine the potential of these phases? In this case, the AQ Plus gives baseline separation straight away. However, the AQ column provides the shortest runtime and also provides scope to optimize. From the previous slide, we saw that the AQ column provided separation of the second and third coelution compounds. However, they were not baseline resolved. By simply decreasing the organic content by 5% in the mobile phase, you can see that the resolution between 2 and 3 is greatly enhanced, achieving more than baseline resolution. Additionally, the resolution between 4 and 5 has increased. So you can see how swapping from a C18 column to another column like an AQ or an AQ Plus can provide alternative selectivity and aid retention for more polar compounds due to the introduction of a secondary mechanism. These columns do also have the added benefit of being able to retain polar alanites robustly under 100% aqueous conditions without testing. So next we investigate SPP columns. What are they and what benefits can they provide to your method development? Until relatively recently, virtually all silica-based HPLC columns utilized fully porous silica particles. The use of SPP columns has been increasing due to their ability to improve column efficiency and achieve faster chromatography. These particles are made of a solid, non-porous core surrounded by a shell of a porous silica material which has properties similar with those of the fully porous silica materials conventionally used in HPLC. You can see in the image that a traditional 3-micron fully porous silica particle is porous throughout the entire particle, whilst the 2.6-micron SPP particle, on the other hand, has a 1.6-micron solid core and also a shorter diffusion path. So what are some of the advantages of SPP columns? With a shorter diffusion path within the SPP particle itself, coupled with a uniformly packed bed and ultra-inert silica surface, reductions in runtimes can be observed. This can speed up method development, improve productivity, and also result in large savings in solvent consumption. SPP columns will often perform at speeds and efficiencies that rival sub-2 micron UHPLC columns, with the advantage of much reduced back pressure. They can be used on traditional analytical HPLC systems with minor modification to optimize the system for reduced dead volume, for example, the UHPLC-like separations on a standard HPLC. Alternatively, you can also do ultra-fast HPLC on a UHPLC system. So who should use SPP columns? They're particularly useful for users who currently use 5 and 3 micron fully porous particle columns who would like to increase their efficiency and speed, but are owners of pressure-limited HPLC instruments, for example, 400 bar maximum pressure systems. You can experience up to 50% improvement in cost and efficiency. Additionally, they are of use to those who are currently using a UHPLC system and are not satisfied with the performance of their sub-2 micron columns. You can get lower back pressures using these SPP columns due to the larger particle size in comparison with sub-2 micron columns, also with robust operation. So there are a few things to consider when using SPP columns. The first is that they have less surface area compared with fully porous particle columns of the same particle size, so the injection volume should be reduced to avoid overloading the column. This will, however, depend on your samples and concentration, as well as your original injection volume. A second consideration is that it's recommended to use sample solvent that is weaker than the mobile phase, which allows the sample to be initially concentrated onto the head of the column and move through the column in a tight band, resulting in sharper peaks and higher efficiency. Additionally, you can run SPP columns on standard HPLC systems, But older systems can benefit from some instrument optimization to realize the maximum performance of SPP columns. Using smaller ID tubing before and after the column, for example, will minimize system dead volume, and therefore the sample dispersion before the column and the peak dispersion after the column. Flow cells in UV detectors can also impact the peak dispersion. Narrow peaks are typically dispersed by larger flow cells, and this will reduce the efficiency and can result in loss in resolution for closely eluting peaks. Use of lower volume flow cells can help to minimize this. A final consideration is that SPP columns are much faster than fully porous columns, and as a result, the peak widths can be much narrower, so the sampling rate should be adjusted to still maintain at least 20 data points across the peak to allow accurate integration. So this brings me on to the Van-Diepter equation to investigate why SPP particles are more efficient than fully porous columns. The Van-Diepter equation describes the relationship between plate height, or H, and linear velocity. The plate height is a measure of column efficiency, and this Van-Diepter equation includes the three main factors which contribute to band broadening, a phenomenon which reduces the efficiency of the separation being carried out. A smaller plate height will correspond to greater efficiency values. So SPP columns have improved efficiency due to the reduction in both the A and C terms of the Van-Diepter equation. But what is actually meant by these terms? Eddy diffusion, or the A term, is used to describe variations in analyte flow path within the column and reflects the quality of the column packing. An analyte molecule within a band of analytes can take one of many paths through the column, and these multiple paths arise due to inhomogeneities in column packing and also small variations in the particle size of the packing material. This tends to make the band of analytes broader as it moves through the column. Eddy diffusion can be minimized by selecting well-packed columns, using smaller particle sizes, and also using column packing material with a small particle size distribution. Due to the manufacturing process, SPP are produced with much narrower particle size distribution than most traditional fully porous particles, and this results in a more uniformly packed column, leading to a reduced A term and therefore higher column efficiency. The C term is the resistance to mass transfer term. Mass transfer is the diffusion of analyte between the mobile phase and the stationary phase, and it takes a short time for an equilibrium to occur between the two. Although some solute is stuck to the stationary phase, the remainder in the mobile phase moves forward, spreading the overall zone of solute. And the quicker this transfer between the two phases occur, the more efficient the separation. Mass transfer effects can be minimized, for example, by using smaller diameter particles, lower linear velocity, and also higher column temperatures. In comparison with fully porous particles, SPP have a reduced diffusion path that the solute must pass through due to the presence of the solid core. The reduced diffusion path will result in sharper peaks and higher column efficiency. So this slide just shows the effect of particle size and the type on the column efficiency, with examples of 1.8, 3.5, and 5 micron fully porous columns in comparison with a 2.7 SPP column. SPP columns can perform at speeds and efficiencies that rival sub-2 micron UHPLC columns on most standard optimized HPLC systems. They exhibit a flatter Van-Diepter curve and can operate at higher optimum linear velocities due to the shorter diffusion distances into the particles. The graph here shows the effect of UHPLC particle size and also SPP particle size on the back pressure when running at different flow rates. You can see that the 2.6 micron SPP column, with it being a larger particle size, exhibits much lower back pressure than all of the smaller UHPLC particle size columns. So you can exceed performance of sub-2 micron particle sizes and also with much reduced back pressure using these SPP columns. An example of the benefits of SPP columns over fully porous columns can be seen here using a neutral test mix, which has been run under the same conditions on both fully porous and SPP C18 columns. You can see that with the SPP column, the peaks are much sharper and taller, resulting in a higher sensitivity and greater efficiency. Additionally, the runtime has been almost halved, which increases the throughput and reduces solvent consumption, therefore reducing the lab expense. The first example for column screening using SPP columns is the analysis of Tocopherols and Tocotrienols. This data was produced by one of our collaborators, Pavel Gornas, a leading scientist at the Institute of Horticulture in Latvia. Tocopherols and Tocotrienols are groups of compounds which are part of the vitamin E family. They are powerful antioxidants and are shown today to potentially protect from cognitive decline. The knowledge about tococriminal compounds is still limited due to several challenges faced in analytical chemistry, and these challenges include separation resolution, coelution, price and absence of standards, and also low analyte concentration in plant material. Application of different column chemistries can assist in the challenges faced in compound separation. SPP columns can also be used to improve separation of these compounds due to the increase in efficiency. In this example, we show the screening of 5 different quasar SPP column phases for the separation of 4 tocopherol and 4 tocotrienol homologs, with focus on resolving beta and gamma isomers. The separation of these types of compounds by reverse phase HPLC typically requires the mobile phase to contain methanol with the addition of 0 to 15% water. The addition of water to the mobile phase improves the separation of these compounds, especially the isomers, and therefore 91% methanol was used as the initial mobile phase for screening the 5 quasar SPP columns of various station phase chemistries. And these phases were C18, biphenol, C18 PFP, an RP-amide, and a PFP phase. The analysis was done using standard HPLC with fluorescence detection, and you can see the results of the screening of these phases on the slide. So let's look into the results of the screening in more depth. The SPP biphenol phase showed poor separation and retention of the 8 compounds with only 3 peaks, and this would likely require quite a lot of further method development going forward. Analysis using the quasar C18 SPP phase provided good separation for the majority of the compounds. However, it failed to separate the tocopherol and tocotrienol beta and gamma isomers. And this phase also provided excess retention, with the runtime being nearly 40 minutes long. This phase is therefore unsuitable for the analysis due to the long runtime and the inability to distinguish between the beta and gamma isomer peaks. In comparison, the SPP C18 PFP phase, with its alternative selectivity and introduction of secondary mechanisms, provided much better separation than the SPP C18 phase, especially for the tocotrienols, which are the T3 compounds. It showed partial separation of the beta and gamma isomers of tocopherol and tocotrienol. Analysis using the quasar SPP RP-amide phase provided good separation of all 8 compounds. However, the analysis time was over 25 minutes, and the second longest out of the columns screened. Resolution between the beta and gamma isomers was greater than the SPP C18 PFP phase, and this could be enhanced further by increasing the aqueous content of the mobile phase. However, this would result in an increase in analysis time. The organic content of the mobile phase could be increased, or the flow rate could also be increased to reduce the runtime. However, this could lead to loss in resolution between compounds, and this was indeed observed when we see this in a few slides' time. Now, when looking at the SPP PFP phase, this shows promising results, as you can quite clearly see 8 peaks. And although not yet baseline resolved, the separation of the investigated compounds was in a relatively short period of time, around 8 minutes long, compared with the other phases screened. So this gives plenty of scope for method optimization, and that will be shown in a few slides' time. Now, the PFP phases are especially useful for separating isomers and closely related species. So to summarize so far, Analysis of Tocopherols and Tocotrienols using a biphenol column was shown to be unsuitable due to coelution and minimal retention. A C18 phase provides much better separation in comparison with a biphenol phase, but it didn't resolve the beta and gamma isomers of either the Tocopherols or the Tocotrienols and had quite a long runtime. The RP-amide and the C18 PFP showed good separation of all 8 compounds in the initial screen. However, when you look at the C18 PFP, the separation of the beta and gamma isomers is not as good as the RP-amide, for example. The Quasar PFP shows promising separation and excellent scope for method optimization with its short runtime. So the SPP RP-amide column showed reasonable separation of the 8 compounds, with compounds 2 and 3 not quite baseline resolved. During the initial screen, you can see that the analysis time was just over 25 minutes, and you can decrease this by increasing the organic content of the mobile phase or by increasing the flow rate. However, when both options are studied, you can see that there is a loss in resolution for some of the peaks. And these are just a couple of examples of investigating after the initial screen. So as discussed previously, the SPP PFP phase showed promising separation and excellent scope for method optimization with a short runtime in the initial screen. With an increase in the aqueous content of the mobile phase, the PFP phase gave the optimal separation of all 8 compounds and complete separation between the beta and gamma tocopherol and tocotrienol isomers, with 85% methanol being used to successfully resolve all 8 peaks on the Quasar SPP PFP phase in 25 minutes. A final example of the benefits of screening other stationary phase chemistries is the analysis of methoxybenzenes. In this example, we look at 3 methoxybenzenes, and as you can see, they are structurally very similar, with 2 of them differing only in the substituent position of one of the methoxy groups. For this method, screening was carried out using a Quasar SPP C18, C18 PFP, and a PFP column. Using the SPP C18 column, compounds 1 and 2 coelute, and there is less than baseline resolution between the coeluted compounds and compound 3. Using the same experimental conditions on the SPP C18 PFP column allows the benefits of changes in selectivity to be realized due to the additional separation mechanisms. A change in elution order has been observed, as well as increased resolution and retention. As opposed to the C18 phase, all 3 compounds show as distinct peaks, and optimization of the mobile phase can be carried out in order to achieve baseline resolution between 1 and 3. And I'll show an example on the next slide of doing this. The same analysis performed on the Quasar SPP PFP phase demonstrates further changes with excellent separation and baseline resolution between all compounds. The same elution order as the C18 PFP phase was observed, and it may also be possible to use a 100 mm column instead of a 150 mm column to reduce the runtime and also reduce the dead time at the beginning. So it's evident from this demonstrated application that switching from a C18 to another phase chemistry, such as a PFP or a C18 PFP, can provide alternative selectivity for closely related compounds. This slide shows how simple optimization of the mobile phase conditions can be carried out on the C18 PFP phase to achieve baseline resolution, and is around 1 minute quicker than the SPP PFP column prior to any optimization on the PFP column. So in summary, the C18 phase is still the workhorse for many applications, but its dominance has reduced as the complexity of samples has increased. And there are now many stationary phases available on the market which hold benefit for various applications. Initial screening of various phase chemistries using the same mobile phase conditions is often one of the most powerful approaches in method development to observe changes in selectivity and improve the likelihood of separating closely related species or difficult analytes in a mixture, as they can provide alternative modes of interaction and retention characteristics. Finally, SPP columns can also provide benefits over fully porous columns in method development, due to their increased efficiency and reduced runtimes, which also increases productivity and provides large savings in solvent consumption. Thank you for your attention, and I would just like to acknowledge one of our collaborators again, Pavel Gornas at the Institute of Horticulture, who assisted in some of the application work.